Hello. Okay, welcome back to the sessions on computational geometry. So today and in this lecture and in the next lecture we will study an object called convex halves. Okay. So let us first define what a convex hull is. You are given a set of points like this. So S is a given set of points in the two-dimensional. Okay. Of course, this convex hull continues to make sense if you go to higher dimensions, but anyway, as we mentioned, we will restrict our attention only to plane geometry. So you have a set of points, let's call that set S. This is the input to the algorithm. Now, CH of S, the convex hull of S, is the smallest region containing all points in S, either in the interior or on the boundary. Okay. So, if I want to solve this problem, for example, in this case, it will be something like this. Maybe I make it a little down so that it looks better. Yeah. As this example illustrates, this convex hull is going to be a convex polygon. In general, this is always true. Why? Because essentially it is the intersection of a finite number of half planes. Why? Take any line. So, if the convex hull lies to the left, then basically this half plane, which is on the left of this, I am considering that. Likewise here, here, here. So, it's an intersection of a finite number of half planes, and each half plane is convex. This is convex, and it is easy to prove that if you have any arbitrary collection, not necessarily finite, any arbitrary collection of convex regions, and you intersect them, that intersection continues to remain convex. It's fairly straightforward to prove, just follow the definition of convexity. And this finite actually implies that we are getting a polygon instead of some other figure. Okay. So, this convex hull is a convex polygon. Okay. Given S, I want to compute this convex polygon. Okay, such that all points in S are either on the boundary, that is a corner of the polygon, or inside the polygon. Like this. Okay. So I have to identify a set of the points, a subset of the points from S which form the boundary of the convex polygon. Okay. Moreover, I need to specify them in the correct order. For example, I may start from the leftmost point and then keep on listing the vertices in a clockwise direction, like this. For example, if this is P1, this is P2, this is P3, this is P4, P5, P6, P7, P8, P9, P10, P11, maybe another P12. Okay. Then my output will be, the given points are P1, P2, P3, this array of size 12, and my output may be P4, P10, P2, P11, P5, P9, P7, back to P4. Okay. So this is the job. So you just imagine that you have an infinitely traceable rubber band. Okay. And these are locations where some pins are fixed to the ground. Okay. This is a pin, this is a pin, this is a pin, this is a pin. And then you have that infinite rubber band. Allow it to settle. Okay. Then the boundary of the rubber band, that will basically be the convex hull. Okay. Fine. So, this is an important geometric construction. We should be able to do it as efficiently as possible. I will come to efficiency issues little later. One thing is that as I ended the last lecture, we will assume that these points are in general position. In this context, that means that no two points have the same x coordinate, no two points have the same y coordinate, no three are lying on the same line. Okay. And then if you choose, you can one by one lift all these restrictions and try to work with a restrictionless environment by modifying the algorithms that I will tell. Good. Okay. Then there is a unique point with the smallest x coordinate because all x coordinates are different. And you convince yourself that that extreme point is, the farthest to the left, this must be a boundary of the convex hull. Likewise, there is a unique point with the largest x coordinate, it's here, P5. So P5 must also be on the convex hull, the boundary. So this is the leftmost, and this is the rightmost. They must necessarily be on the convex hull. Now, if I start traversing the hull from the leftmost point and follow the hull boundary, I'll eventually reach the rightmost point. This part is called the upper hull. So our traversal is always clockwise. Let us see. So, from leftmost point to rightmost point, the part of the hull, this is not still a full polygon, a part of it, this is called the upper hull of S. Okay. Likewise, if I start traversing from the rightmost point, follow the clockwise order, come to the leftmost point, from rightmost to leftmost. This is called the lower hull. So, rightmost to leftmost, this is the lower hull of S. Okay. So, one thing is clear, if I am given the hull, I can definitely, if I am given this complete convex hull, so CHS is nothing but the upper hull followed by the lower hull. So, if I am given the full convex hull, then I can extract the upper hull and the lower hull from it. Conversely, if I am given the upper hull and the lower hull, I can easily stitch them together in the form of the complete hull. Okay. So, it also, because of, I would say, symmetry, any algorithm that constructs the upper hull analogously works for the lower hull. Right. These two constructions are very similar. Therefore, in many algorithms, I will assume that I am constructing only the upper hull. But there will be some other algorithms where I construct the complete hull. But there is no harm in assuming that the algorithm is restricted to compute the upper hull. Fine. Okay. I think this is fine. The definition should be clear. The smallest convex polygon and its corners are some sub-collection of the input collection of points. And I have to specify them, maybe starting from the leftmost point and following the clockwise ordering. Okay. So, we will study several algorithms to solve this problem. But before doing that, let me prove some complexity result, some lower bound. So, the theorem is that assume that this input set S contains n points. Then it is impossible to construct the convex hull of S in small o of n log n time in the worst case. Okay, so this is small o, not big O. So, this is very similar to the comparison based sorting problem, which cannot be solved in small o of n log n time. Okay. Why? So, using this result, you must expect a running time of at least big O of n log n for any convex hull algorithm. You cannot do anything better than that. So, you have to accept this reality, but let me prove why this is the case. What makes it hard in that sense? Okay. So, while proving a lower bound on sorting, we use something called a decision tree, some permutations, factorial n, take log of that and all that stuff. But usually we do not do some such generic proof. Instead, we do reduction to prove lower bounds. Okay. And this is basically the same idea of reduction as in Turing machines. You all know, right? Proving something difficult uses reduction. Not necessarily you always use something like the diagonalization argument. Okay. That's usually difficult for most problems. Now, suppose, why is it? It is the case. Suppose my ith point is x. Okay, sorry. Okay, so I will use reduction. So, reduction from a problem which is known to have this lower bound. Okay, so that is something like sorting. I will reduce it to the problem of computing convex halves. Okay. Now, what is an input to sorting? This is an array x1, x2, xn. So, without loss of generality, I can assume that these points are distinct. Yeah. These points here, x1, x2, they are all different. I want to sort this array. Okay. So, I will now convert this to a set of points p1, p2 up to pn. And I will compute the convex hull of these points. This will eventually give me a sorted version of this array x1 through xn. Okay. So, if I can convert this instance to this in less than n log n time, in fact, we will do it in big O of n time, linear time. And if from the result of this convex hull algorithm, I can obtain the sorted version, again we will do it in big O of n time. Then what happens? If this is solvable in less than n log n time, in the worst case, and the reduction takes big O of n time, then this sorting can also be solved in less than n log n time in the worst case, which we know is not possible. Okay. So, what is the construction? Construction is very simple. From the point xi, I will consider the point xi comma xi square. Okay. This is the construction. So, it's a matter of just multiplying xi with itself and generating this point O1 time for each I. Therefore, for this n points, this conversion takes big O of n time, big theta of n time to be more precise, but anyway, that doesn't matter. So, why does the convex hull of these points give me information about the sorted array? So, all these points lie on the parabola y equal to x square. Right. So, how does the parabola look like? So, it is something like this. So, my points will lie on this. Something like this. Maybe this is P1, this is P2, P3, P4, and so on. P5, P6, P7, P8, P9, maybe. Something like this. Now, if I construct the convex hull of this, it will be P8, P3, P5, P1, P6, P2, P7, P6, P9, P9. So what is this? Let me write down. P3, or maybe I start from P8, P3, P5, P1, P6, P2, P7, P9, P8. Back to P8. Okay, I don't have to write it, it's implicit. I'm coming back to P8. Did I miss anything? P3, P5. What is missing? P4 is missing somewhere. Oh, P7, P9, P4. Okay. Then, if I take their x coordinates, there will be x8, x3, x5, x1, x6, x2, x7, x9, x4. Okay. So if I just move this x8 to the back, then you can see that x3, x5, x1, x6, x6 is already in the descending order. Now it's just a matter, so just I move x8 from here to here. Then these points are already in descending order. Descending sequence. And then after this we will just reverse this array. This is another big O of n time exercise, right? So, given this, construction of these points can be done in big theta of n time, and whenever you get your convex hull from the leftmost point, something like this, then you just extract their x coordinates, which will be same as these points, these numbers, okay? And with little bit of processing, you get the array in the ascending or descending order, whatever you want, okay? So, this reduction takes big O of n time. Therefore, if there is an algorithm for computing this convex hull which runs in less than n log n time, I have an algorithm for sorting which runs in less than n log n time. Of course, all these running times are worst case running times. This is impossible, and therefore, any algorithm that computes the convex hull must be prepared to accept a running time of big O of n log n. Okay. And any algorithm for convex hull which runs in big O of n log n time is therefore optimal. Right. Good. So, we will study 4 algorithms, and one by one, in each step, we will see how we can improve the performance of the algorithm. So, I will talk about the first 2 algorithms. These are simple ones, and in the next lecture, I will talk about the 2 remaining algorithms. Okay. So, for all these algorithms, yeah, I think for all, we will use some results that I told you in the last lecture, site P1, P2. It essentially says that given the oriented line segment from P1 to P2, what is the relative position of P with respect to that oriented line? Okay. For that matter, we compute a 3 by 3 determinant, 1, 1, 1, x1, y1, x, sorry, x1, x2, x, y1, y2, y. This 3 by 3 determinant we compute. If it is 0, P lies on that segment. If it is positive, P lies to the left of that segment, P1, P2, in that oriented segment. And if it is negative, P lies to the right. Okay. So, all these algorithms use this. So, I start with the first algorithm, which I call a naive algorithm because it uses this site computations rather naively. And its performance will be quite poor. So, we will slowly improve the performance of convex hull algorithms. So, let us think of a convex hull like this. There are many other points inside. Okay. Now, I can identify an edge of this polygon, okay, by using this result, which is almost obvious. So a point, PQ, but P and Q are two given points, is an edge of CH of S if and only if all points of S except of course P and Q lie to the same side of the oriented segment PQ. Okay. For example, same side means either all are to the left or all are to the right, and it depends upon your orientation. If I, for example, consider this edge, this is my P, this is my Q, then all points except P and Q are to the, this is left, right. On the other hand, if I consider this orientation, Q to P, then all other points are to the right. Okay. So we will compute the side computations, and if all sides are positive or if all sides are negative, then I identify PQ as an edge of the convex hull. On the other hand, if I look at some non-edge, something like this, or this, or this, then you see that some of the points lie to the left, some of the points to the left, some of the points lie to the right. Okay. So this is a complete characterization of all edges of the convex polygon called the convex hull. Okay. Therefore, if I use this in order to identify all the edges, what should I do? The procedure is very simple. For all P, for all R, for all Q in S, Q not equal to P, for all R in S, R not equal to P comma Q, and then we write the code, compute side and check whether all the sides are P, Q, R, and then some check. All the sides are of the same sign, then you include PQ as a potential edge, as an edge of the convex hull. And once you get all the edges, it's a trivial matter to stitch them together in a clockwise listing. Okay. So after this, stitch the edges identified to a list of vertices. This is actually an easy part. Okay. So the big question is, what is the complexity of this? P in S. So this is a big O. P contains n values. Sorry, small n. I am using small n. And this is n minus 1. And this is n minus 2. And whatever computation you do here, this is big O of 1. And the stitching may be done in big O of n time. In any case, identification of these edges takes 3 nested loops, which runs for n or nearly n iterations. So the running time of this algorithm is big O of nq. Agree? And that is quite poor, because n log n is far away from n cube. So we have to do some more serious tuning of this algorithm. Okay. So I will tell you another naive idea, which also works by detecting edges, but in a much more intelligent fashion. This has 2 implications. First, the running time reduces to big O of n square. Second, In the best case, it may even run in big O of n time, linear time. So, that second thing, second algorithm, which is again essentially the same idea, identify the edges on the boundary of the convex hull. So, this second algorithm is called Jarvis March. Okay. So, let us see what it does. Suppose that, okay, it not only identifies those edges in any haphazard manner, it will start from the leftmost point and keep growing the hull by identifying the next edges like this, or maybe from your side, this, something like this. Okay. So, what happens is this. Now, you have a set of points like this. Okay. Then what you do, maybe you start from the leftmost point, you discover this edge, you discover this edge, and then let us see how the next edge is discovered. Okay. To that effect, what this algorithm does is that, assume that at least two edges, at least one edge is added. Okay. So what will happen when I am here, I will explain little later. Okay. The first iteration actually. Okay. So what I will now do, okay, let us call this P, let us call this Q, and consider this ray PQ. Now compute this angle, 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 right? For all the remaining points, except P and Q perhaps, you don't need to compute the angle PQ with Q or P, but otherwise this, all other points. Okay, so there are n minus 2 of them, you compute all these angles. And in the first class, you have seen that, given a situation like this, you have P, you have Q, and you have R here, then I can compute this angle by a couple of A, tan, 2 calculations and using some cos, sine and all that stuff in big O of 1 time. Now, if I consider the angles in the clockwise direction, then the next point R should have the largest angle with respect to this PQ, with respect to PQ. And if I construct the angles in the clockwise direction, which is nothing but 2 pi minus the counterclockwise angle, then the point that gives me the smallest angle will be the next point on the boundary of the convex hull. This is clear, right? Compute all the angles, maybe in the clockwise direction, and choose the point having the smallest angle with respect to this PQ, this ray. Okay. Okay. Maybe for computing actually, I am computing this angle. Okay. So then I can find a point here, a point like T. That's fairly straightforward, like. So 1 minus T plus TQ. All points of this form are on the line. Therefore, and if I take a value of T which is bigger than 1, this will give me a point here. Then I can compute this angle. Okay. And so, if I take t equal to 2, then t will be minus p plus 2q. So, this is a point that will definitely lie on this line, but this direction, and then I can compute this angle. Okay. Fine. No problem. And then I choose the point with the minimum possible angle as the next point on the boundary of the convex hull. Right. Keep on doing this until eventually you will come back to the point, the leftmost point from where you started. Okay. So keep on discovering. Next points on the boundary. Until the leftmost point is reached. You start from there, eventually you come back again to the leftmost point, so you are done. The only question that remains to be answered is what will you do for finding the second point? Leftmost point will always be there. What about the next one? So you need something like this PQ line, but in this case you use the vertical line as your reference. So this will work. Right, this will work. What this PQ is doing here is vertical line. Okay. And again you see why it is somewhat important in this algorithm that no two points should have the same x coordinate. Okay. This will imply that I do not have another point on the boundary of the hull having the same x coordinate. So this is a good thing. There is a unique leftmost point. Okay. Now what we will do if you allow x coordinates to repeat, I leave it to you as an exercise. It's fairly straightforward. Okay. So from time to time what I will do is see that my pictures are horrible. Okay. My handwriting is also horrible, but pictures are even more horrible. Okay. So what I will do, I will sometimes give you better pictures like this. Yeah. So this is, yes, it's something like this. Initially you start with this reference line which is vertical, then keep on growing the convex hull by discovering next points, and suppose at some point of time you have here Q, and the last point discovered before Q is P. And then you compute this angle, the angles of this directed ray PQ with all the remaining points. That is this angle, this angle, this angle, this angle, and so on up to this point, this angle. Okay. And identify that point which corresponds to the smallest angle. Or if you compute angles in the counterclockwise direction, pick the point extending the largest angle. Okay, so it depends on which direction you are computing the angle. In this case, it turns out to be R. So you know that after Q, R is a point, R is the point on the boundary of the convex hull. Then you will discover this one, and eventually you come back to the leftmost point, and that is the end of the algorithm. Right? I hope this picture makes it much better sense than my horrible drawing on the board. Good, right? Fine. So I once again come back to blackboard mode. Okay? So control up. Good. Okay, so now for the rest of today's lecture, I will deduce the remaining analysis of this Jarvis March algorithm and talk about its implications. Okay. First of all, running time. Each step in the march computes n-2 angles. Correct? So each step in the march involves two things: computing n-2 angles. Each computation, as we have seen yesterday, or I would say the last lecture, it can be done in, each angle can be computed in big O of 1 time, so it is big O of n time. And finally, you have to extract either the minimum or the maximum, depending upon in which direction you are computing the angle. This is for clockwise, this is for counterclockwise. So, one max or mean calculation among this n-2 computed angles, and this also involves big O of n effort. So, each step finishes in big O of n time. Okay. And if your final convex hull contains h edges, then this algorithm is big O of n h time. Right. So there are several things to consider about this running time. It's a, I would say, interesting thing. For one thing, okay, so let me write one by one these three implications of this running time. First, worst case. So running time is big O of nh, where n is the number of points and h is the number of edges on the output hull. First is, in the worst case, h can be as big as n. It can be n by 2 also. In either case, the worst case complexity of Jarvis March is big O of n square. Okay. So, although this is better than your O in big O of n cube time naive algorithm, this is still not optimal because optimal algorithm will run in big O of n log n time. So, we have to do something more. But what is more important, if h is small, like in the case h is big O of 1, the complexity is big O of n, and this is already better than n log n. So, can h be so small? Yes, you can think about something like this. Maybe you are given something like a pentagon. Okay. You are given a collection of points which contains the 5 vertices of a pentagon and many other points in the interior of the pentagon. And your task is to identify the edges of the pentagon. Okay, so you have to identify this. So if you run Jarvis March on this collection, then after 5 steps in the march, you will discover these 5 points which are on the corners of the pentagon. So if you are in such a situation where h is small, then your algorithm may be even better than n log n time, but definitely this is a good or best case complexity. Worst case is still big O of n square. Okay, so this is achievable, but in the best case. Okay. And the third thing about this running time is that it depends not only on the input size, which is n, it also depends on the output size, which is h. Okay. Any algorithm whose running time depends not only on the input size but also on the output size is called output sensitive. Okay. Because the output running time is sensitive to the output size. Okay. In particular, Jarvis merge is an output sensitive algorithm. Okay. So, running time depends on both input size and output size. Okay. Perhaps you have not seen many examples of output sensitive algorithms, but in geometry, output sensitive algorithms are not so uncommon, I would say. And therefore, typically, geometry, when you study geometric algorithms, we talk about output sensitive algorithms. Okay, so from n cube to n square, with a good bit of luck, we can even have big O of n. In particular, if h is big O of log n, then I have already reached big O of n log n time, but this is still not good in the worst case. So I have to do more work in order to reduce the complexity to n log n. So in the next lecture, I will cover a couple of algorithms which achieve this big O of n log n time in the worst case. One will be iterative and the other one will be recursive, similar to merge sort. Okay, so let me stop for the moment. In the next lecture, I will introduce the two optimal algorithms, and that is all about convex house. Then we will study other topics from geometric algorithms. So, until then, goodbye. Again, meet you in the next lecture.